Hi, I'm Malika. I'm very excited to present this work with my fantastic co-authors, Yupeng Huan from the University of Rochester and Korganbekova from Harvard. So the project is about ranking algorithms and equilibrium prices. So when you shop online and you search for a particular product, you see a search result page, which is usually constructed as a math matrix, as a product grid. This page is called ranking page. Now, there are ranking algorithms that decide which products will appear on these pages and in which order. And from the current literature, we do know that top-ranked products, they get a lot of consumer attention. And what that means is that they get a lot of clicks, a lot of purchases, and this leads to this notorious feedback loop in ranking algorithms, where essentially the top products get a lot of consumer attention, and that's why the next period, the ranking algorithm again prioritizes those products. Now, this has been a reason for worry from platforms and policymakers. Mainly, the problem here is that now that the top products are always at the top and are very hard to displace, the sellers of those products have more bargaining power and therefore can raise their prices. And so what that means is that ranking algorithms may decrease consumer welfare through changing competition environment on the platform and through higher prices. But at the same time, it's an open question as to whether ranking algorithms that we all see on Amazon and on different other e-commerce platforms, whether they affect prices, and how do they affect prices, and how much power does the platform have over the competition on the platform through this algorithmic design. And that's exactly the research questions that we're going to be studying. And given how large the search literature is, you might think that we already should know the answer to these questions, right? But it's not necessarily true, because what we know is that ranking algorithms and rankings in general, they shape demand and consumer welfare. A very close paper to ours is Aaron Kay's job market paper, where he basically says that as a result of personalization, the consumer's demand elasticity changes, and now the sellers have this opportunity to raise prices. Justin Huang's paper, job market paper, is about the fact that a particular style of ranking algorithm on app stores could lead to lower introductory pricing. Now, a different strand of literature basically says that algorithm design can directly shape pricing incentives if the prices are a kind of an input to the algorithm. What our paper is about is something different. What we are interested is, what is the impact of a non-personalized ranking algorithm that does not necessarily bring a better matched product to the consumers, and that does not necessarily incorporate prices in it? How does that impact equilibrium prices on the platform? Okay, so to make sure that everyone is on the same page, I will explain the empirical setting here. So as an empirical setting, you could think of Amazon or Walmart Marketplace. So they create a website. Their job is to match consumers and sellers. The seller's job is to set wholesale prices. The platform then applies a percent margin, and that becomes a retail price. Now, on the consumer side, consumers' demand is a function of prices, but it's also a function of the way the products are ranked. And when I say prices, from now on, I mean sellers' wholesale prices. For simplicity, you could think of like a percent margin being some fixed percent margin that the platform applies. So basically, at the end of the day, what matters is the seller's wholesale prices. Now, our object of interest is the causal impact of ranking algorithms on equilibrium prices. And this is a very hard question to answer for several reasons. The first reason is that ranking algorithms are very much a black box. As research, we usually don't know what's inside the algorithm, what is the input, how does the algorithm work. And second problem is just simple endogeneity. Everything is super endogenous on these marketplaces, where demand is a function of prices and rankings. Rankings themselves are a function that maps historical demand into ranks. Prices also depend on historical demand. So basically, everything is a function of each other, right? So everything is super intertwined. And now the question is, how do we find out the impact of this ranking algorithm on prices? Go ahead.
Conceptual question based on what Joel is saying, right? So in practice, these rankings are determined through some sort of reinforcement learning type algorithm. And so I could already show like why does it matter? I could just try different things until I figure out which leads to the highest revenue.
So our point is slightly different in this. So we are going to be doing something similar. So in the counterfactuals, we are going to simulate a different ranking algorithm. We basically are going to change a portion of ranking algorithm to simulate the counterfactual prices, like the ones that will decrease prices, increase consumer welfare, and stuff like that. So I think what you're saying is that from the platform perspective, I could be tuning my algorithm to the point where I'm maximizing revenue. And that's partially what they're probably doing, but it doesn't eliminate the question of like, how does it still impact the equilibrium prices on the platform and sellers' incentives?
So why not? I mean, I can do reinforcement learning with equilibrium prices as my object that I'm trying. But I can use reinforcement learning algorithm for anything, right? And so like I don't just have history's demand, I have history's prices.
Yeah. So the platform that we're collaborating with has a Bayesian ranking algorithm. It doesn't have the reinforcement learning. Theoretically, yes, you could tune the algorithm as to if your goal is to decrease prices, you could tune it until the prices are the lowest possible. But from the economic point of view, we still want to know, from the policymakers' perspective, we want to know what is the impact of this on equilibrium prices, because for your point, it kind of it would necessitate that the platform has lower equilibrium prices as an objective, right? If I understand it correctly.
I guess Joel can speak this more than I can, but what most platforms do now is they say like, here's some outcome object I really care about. Right? I'm going to use a reinforcement learning algorithm. I'll run it in an A/B test. I'll see what happens. Which incidentally reduces exogenous variation ranks and everything else.
Right.
Then depending on that, right, there's another algorithm, just sort of iterate until I find and learn sort of the
for sure.
economic quantity interest, which could be prices, it could be demand, it could be revenue.
So I
guess my point is like, is this a hard question to answer? Why can't I just bumble across the state space to find the? By the way, it's a conceptual question. I'm not criticizing this. I'm just saying like in practice, what I love to hear Joel's perspective.
That's way that has reinforcement or retreat. That's what.
Yeah. But so you can go ahead.
Can I maybe rephrase that? So if you're interested in like equilibrium prices or sellers respond to the structure of the algorithm, then you would need to wait until the market really equilibrates, right? At 15 months or years. So every potential option you try, different parameter you set, you would wait for months. So that means just pure exploration is probably
It's incredibly sample inefficient. That's the value of the structural models. I think it was. I mean, that I've seen. I read a paper. I don't know. Some people tell me. But if you the estimated quantity from the paper showed that to get the same parameter via like reinforcement learning, you have to like use more time than the history of I don't know, like the whole universe basically. There's a structural model.
Yeah. So
you're learning over wholesale prices and demand in your reinforcement learning model, not just wholesale prices.
Yeah. So basically, if I'm a researcher or a policymaker, I really don't know what is the ranking algorithm that the platform is using. So what the platform does inside, it's still like going back to your friend's point, like again, the market equilibrates like in the long term. So we don't know that. So. But you're definitely right. They are tuning it. Yeah, for sure. The objective function is very different, though, and I'll talk about it in a second. So to understand the impact of ranking algorithms on prices, we have two options. We either need, like back to Carl's point, an exogenous variation in the ranking algorithm, right, where the ranking algorithm is randomized, or we need random changes in the histories, in the historical demand, in the inputs to the algorithm. And technically, it's not very hard to change the ranking algorithm, but the point is that like you have to, back to also Carl's point, like you kind of have to keep changing the algorithm and you still don't know the long-term equilibrium consequences of that. And so what is going to be happening in this paper is actually the second portion. We're going to be changing exogenously the historical demand. And it might sound very crazy, but that's exactly what's happening in the paper. So what we do in this paper is we know the platform's ranking algorithm, we know the objective function. The objective function is not to decrease prices. The platform is maximizing the purchase probability. It's a Bayesian ranking algorithm that basically ranks products by posterior conversion rates. And we observe the algorithm's full internal state, like priors, posteriors, and variances. And the platform, we did not participate in it. The platform itself ran an experiment that randomly boosted products' priors. So that's what I mean by basically boosting historical demand. So they pretended as if demand occurred to the products when it actually didn't, right? And so that leads to random boosts in the product rankings, and that gives us the opportunity to, like this exogenous variation, to study the causal impact of ranking changes on prices. And then we still need a structural model to explain the mechanisms and to run the counterfactuals to understand what is the mechanism. I'm so sorry, Joel, that you have to go through the structural model, but I was very much aware that I was the last to present today, so it's going to be live. Okay, you will see a live version. Okay, so in terms of the preview of findings, so what we find is that the random improvements in the rankings, contrary to what platforms or policymakers were concerned about, they didn't increase prices. In fact, it was the opposite. The sellers whose products were randomly boosted, they decreased their prices. And what our structural model and some experimental analysis shows is that there is some dynamic investment incentive on these marketplaces, where from the seller perspective, I think, okay, I have to decrease my prices today in order to sustain my rankings tomorrow. So they're not playing a short-term game, they're playing a long-term game here. Srinivas.
What do you think by improvements in the ranking? What are the improvements?
Oh, I will explain the ranks themselves. I will show you more.
What is the objective?
I'm sorry?
What metric are we using to determine improvement? Oh, improvements.
Sorry, in boosting of ranking.
So this price curve, how long run is it? Because there is this possibility that I say, okay, my rankings are not, I'm going to reduce my price, I'm going to get good share. And then after that, I have a good amount of share, I would increase.
That's a great point. So I will show you the graph that basically tracks down long term, and we do see that it is persistent, it changes. I saw the hint there.
So what do you think that these companies are thinking? They suddenly see, oh, I got an exogenous boost in my ranking. Like, do they think I'm doing something good, or either my competitor is doing something bad, or it's something, some A/B test that this company is doing?
So from the seller's perspective or from the platforms?
From the seller's perspective. So the seller who eventually cuts prices. Does it matter whether this cutting the prices is because of some exogenous thing or because of some change in the algorithm?
No, very good point. So we don't know what sellers' beliefs are technically, but we do know that sellers actually do constantly monitor their ranking position. So they do see if they're boosted in the ranks, they do see that. And they do understand the kind of, they have a high level understanding of what the ranking algorithm does. And they do understand that potentially, if I decrease my prices, there is some possibility that I will be sustained tomorrow. If you're asking whether they know that the experiment is running, it was not explicitly told.
Yeah. So again, just a response to Joel reflect on this. What are equilibrium prices? That they're mapping from states prices. It's a rule I'm trying to learn. Those states are ranks and demand. Right? That's what I'm mapping. So to me, what reinforcement learning is really good at doing is learning rules because it tests and learns.
Right.
But it's like I would think that if my goal is to sort of learn the equilibrium pricing rule, that reinforcement learning would actually be really good. Not slow to converge faster.
I mean, what you also do, right, and you run offline reinforcement learning, right? So much of my work is that when I didn't like, I mean, that's also structural modeling, right? If you ask some people, like in the stats community, they would call that structural modeling, but it's not structural economic, right? So we do run like offline to do that as well, instead of actually experimenting. Then of course that isn't as reliable.
Malika, you're going to give us some sense of how long does it take for this to
2%.
Yes, I will keep going with this. Thank you. So in terms of, so this is a preview of findings, and now I'll talk about the data. So we partner with a major US e-commerce platform. There is one consumer durables category that we work with. So think of treadmills, TV stands, something durable. There are more than 100,000 products on the in the category, and more than 2,000 sellers, almost 2,000 sellers. The data covers the period from November 2021 to February 2023. There was no personalization and no sponsored ads in our data set. Again, two key advantages of this setting is that we do observe the ranking algorithm, and we know that and we have this experiment where the platform randomly shifted algorithmic inputs. Okay, so let me explain, since there were so many questions about the ranking algorithm, I want to explain to you like at a high level what they do. So it's a Bayesian ranking algorithm. Suppose the platform needs to rank 4 products. What they do is something quite intuitive. And a lot of platforms actually do the same, just like different models. So they're trying to predict for each product J at time T, they try to predict the conversion probabilities of those products. So purchase probabilities. You could think of it as number of purchases divided by number of impressions. Impressions means how many consumers viewed this product on the ranking pages. And then the products are ranked in descending order of this posterior conversion probabilities. That's it. That's basically the high-level intuition of the algorithm. And now suppose like period 0, the platform has no idea what's happening. And so they can basically randomly rank products. But eventually at period T, consumers start coming to this products, right? So the impressions realize, the purchases realize, and now the platform can calculate the posterior conversion probabilities. Okay, and then we basically know the posterior conversion rates, and there is some uncertainty about these posteriors. You could think of it as, if you're thinking of like beta, we will approximate it with beta Bernoulli approximation. Okay, so the first observations that we make from the data is that top products get a lot of attention, right? That's what I told you in the beginning. So basically, what you see on this graph, the x-axis is the rank in median consumer session. So each page usually has 50 products. So basically, first page products get almost 80% of impressions and 90% of sales shares. Obviously, this is partially endogenous, partially causal, similar to rollable space.
I have one clarification question. Is there any optimization for the page? It seems like there is not.
No, there is not. There is not. So basically, what they do is they optimize 192. Like basically, they choose certain number of pages that will be shown. Okay.
When the page is going to be rendered,
right?
If you just is there a concern that if you just rank by conversion, imagine brands, right? Mm-hmm. If Samsung ranks high and just gonna have Samsung,
That's right.
Samsung, there's no variety happening there, and you want to have some, if you care about consumer experience, you probably would, at the page level, you don't want to just rank by click-through rate or conversion. You want to account for the assortment.
For the diversity. I think
you're saying that's not the case.
That's not the case. That's not like the similar case would be Yuyan's job market paper, mm-hmm. right? Where there is like diversity objective included. This platform does not choose.
And it doesn't lead to, are we in the product category where there's brands, for instance?
So this is the thing. It's a very horizontally differentiated category. So it's not like some brand is dominated. Yes. So that's why I don't think it's a concern. Okay. And then when a new product gets introduced, it's very hard for this product to move up the rankings. That's the second observation we make. So the average product, when it's introduced, it's usually on the 7th page. The median product is on the 3rd page of the ranking results. And just now I showed you that all the actions are coming at the first pages, right? And so what I'm plotting here is the algorithm's posterior conversion rate. The blue line is the mean posterior. So basically, as product gets introduced, they don't start from 0, because they cannot start from 0, they need to calculate something. So there is a slight boost here, but then over time, the product's posteriors usually decreases, and especially bottom 10 percentile of products, their posteriors decrease, and only 90th percentile of products sustain their rankings. So it's very, very hard for an average product to kind of get at the top of the ranking page results, but obviously the payoff of that is very high because they get a lot of attention. Okay, so now let me talk about the field experiment. So the platform boosted this prior conversion probability for the product. Like literally, you could think of it as like mechanically adding some number to the posterior conversion probability as if the purchases occurred when they actually did it. And that leads to exogenous ranking improvements. Okay, so in terms of the design, products were chosen randomly. They were stratified into 5 groups. You could think of it as like 5 quintile groups. Groups 1 to 3, 10% of products were treated. So 10% of products were boosted, 90% of products were left as is. Groups 4 to 5, all products were treated. And so we have this random variation in groups 1 to 3 as to like the percent of products that get treated. And then we also have the staggered design. So basically each quarter around 2,000 products get treated, and this treatment timing is not strategic. So there is literally a person who is responsible for this experiment, and they would just like boost products whenever they want. It's like definitely not strategic. We talked to this person. The only constraint they had was like holidays and Prime Days type events, right? That's when they couldn't boost, but otherwise it was quite.
So how many products are simultaneously being boosted?
So per quarter, it's like 2,000 simultaneously. I don't remember off the top of my head, but it's like hundreds of products. But at the same time, because the category is so large, it's a small percentage of products, so that there is like not a lot of super violation. I think this. Oh, okay, go ahead.
Yes, I know that only 2% of the products are boosted, but if you only look at the top few positions, that still, manifests as a big change from the, consumer's perspective. So if you believe, prior to this rearrangement, there's this optimal state, and then you somehow disturb it, could that, effect somehow coming from this total reduction in demand, so to speak, or
so we don't observe total reduction in demand. I think what you're worried about is also SUTVA in terms of like if you're treating, like if you're boosting products into top positions, then like neighboring products are impacted, they're cannibalized and everything. We did check, like it's very hard to define a neighborhood here, but because it's like so horizontally differentiated, but basically we do not see any impact on neighboring products. We do have that in the appendix. Cool. So first thing that we need to do is obviously to validate the experiment. So first of all, we look at the posterior conversion rates. So after treatment, we do see that there was a large and permanent increase to algorithms prior, right? So literally at the treatment timing, algorithms posterior conversion rate suddenly increased out of nowhere. And it wasn't like it decreased the next day back to the normal. No, it was quite persistent, like over time. Okay, and so next thing is if we look at what were the like market impacts for this product, what we see is that boosted products rank number decreased by 166 because like usually it's 50 products per page. You could think of it as like each boosted product is moved up by 3 pages. It's huge, right? I told you that the median new product is on the 3rd page, which means that they're basically on the 1st page.
Does this platform have a sponsor product?
They do not have a lot. They do not. No. It's not Amazon, so no.
Come on, man. There's money to be made.
I know. I tell them that all the time. Anyway, so impressions increased significantly by 158. And the baseline numbers are very small, the mean dependent variables, right? And the purchases increase. So in that sense, basically, definitely there is some impact going on. What we were interested in is the wholesale price changes, right? As I previously mentioned to you, and what the previous literature also found, is that technically the prices should have increased as a result of this boost in demand. Instead, we observed that the prices decrease. And I omit the picture here. So basically, this 2.3% decrease in wholesale price effect is quite steady over time. We look over 40 weeks after the treatment, and it's still quite stable. No?
Why is the effect so immediate? You think that it takes some time for the sellers who are displaced to
Right.
learn and how to, kind of invest in lower price in order to kind of full coverage. Right?
No, that's a good point. So first thing is like we shadowed some of the sellers. Basically, some of them they're very like they're really monitoring their products. So they will see if they're because the rank number increase was so sudden. They're like, oh, okay, I'm 3 pages high now. Like, what do I do now to stay there? Like, and so in that sense, they are actively monitoring those products, right? So that's why the reaction can be, and it's also not super like the x-axis is in weeks, so it's like it takes like a couple. Right?
Do you know by any chance that some of the sellers are using algorithmic pricing tools by any chance?
That's a good point. To my knowledge, no, but I will check. We will check. Yeah, go ahead.
Oh,
Go ahead.
do you feel conversion rate is an objective thing that you can form posterior believe on, or is something that is past dependent as well? For example, if for certain product that start with like very low ranking, it might be a niche product, if conversion rate can be very high because even people have impression on it, they will purchase. But when you boost it up, you may not have as high conversion rate as it was because I mean there are certain components.
That's a very good point. That's actually true because like if you boost some product that had a very high conversion rate and then the number of impressions is increasing, but if purchases are not changing, then your conversion posterior will decrease, and that's what we see. That's true.
Yeah, then if conversion rate is past dependence, how do we form a posterior lever?
I'm sorry, I'm not following the question. Like you just literally calculate the number of
Remember that like conversion rate is actually a function of how you are being boosted or how you are being dragged and where you start from, all the things. I mean,
sorry, boosting. We can talk offline.
yeah,
I feel like you have maybe a deeper point here. Boosting is that like literally mechanical change to conversions. Really? Yeah.
Yes, okay, sure. The results, which is the solve, you're not saying it's possible.
No, it is possible because it's an experiment.
Oh, okay. Okay, so two things, I guess. I'm trying to make sure that I
Yeah, sure.
Well, the first thing is, I think that Bob was asking this earlier. So this is at the product level, right? It's gonna
Right, yeah.
done it. And it's in the same time,
Yes.
which means there are substitutes to this problem, to the treated products.
That's exactly Meng's question, right? In terms of like the SUPA violation.
So,
Yeah. So we do check for the like whether there were significant changes in like neighboring products rankings and whatever, and we do not see the effect.
And so the second thing is, this is a staggered. This is 286 effects. I know that.
Oh, we do check the Callaway Santana. Don't worry. Yeah. Yeah. Justin?
Just another point on the SUPA. So it could be the case that like a large, like long tail or not very popular products are very effective in their position. But you can imagine that like a one position change at the very top of the rankings then shifts like a large amount of impressions. I don't think you showed the analysis that you've done. Is it sensitive to that? The fact that like a small number of products can be very largely affected and a large number of products are probably not affected at all.
Oh, so you're saying that like eventually it will be averaging out somehow? I see.
No, more like the competition is really at the top. Like going from like 2 to 1 is probably like a 50% bump in impressions. Whereas like the vast majority of our observations are on like page 7. And even if like a bunch of stuff comes past us at page 7, we're still getting like nearly 0 impressions. Then like some potential analyses would say, oh yeah, there would go in that.
So we can I think like the big thing here would be like page level analysis. Like maybe we can do that. Technically, honestly, I'm not very worried about SUTVA because we checked a lot of times and there was no no significant spillover effects because the competition is so it's such a horizontally differentiated area. I'm so sorry. I think I have to finish at 5:15.
Approximately.
Let me maybe take one more question and then I will.
30-second meditation.
Maybe.
I think.
Yeah. So I will then take one question and then I will move on so that we have time for time.
I guess I sorry to ask one more super question,
Sure,
but
sure.
doesn't the intensity of treatment depend on, shouldn't that be heterogeneous? Like, yes, everyone is boosted initially, but then a product that you learn is a really good product stays high for a long time. But the product, like the treatment effect you're measuring is of the initial boost, but you're averaging over a bunch of different dosage intensities based on how long they're stuck at the top.
Oh, that's definitely true. We could do some differential analysis in terms of like heterogeneity.
But something.
That's a good one.
That's a-
Yeah, cool. Thank you. So given that this there is this decrease in prices, the question is, why is this happening? Like, what are the potential mechanisms here? So one mechanism could be seller behavior. Maybe sellers are inexperienced. Maybe they didn't realize what they were doing, right? Second story could be a standard static story where the demand elasticity may be very different at different ranking positions. This is similar to Adam K's job market paper story, right? So maybe when boosted, products face a very different demand, and therefore they have to decrease their prices. And finally, another version would be a dynamic story where maybe sellers have know something that we don't know as researchers, and maybe they're trying to invest and sustain their rankings in the future. Okay, so let me go, I'll go with the first two to eliminate them, and then we will talk about the dynamic story in more detail. So to understand whether it's something driven by the seller behavior, we basically do the following. We look at the two-way fixed, we run this two-way fixed effect regression with interacting with the experience proxies. So the experience proxies for us are the tenure, number of years the seller was with the platform, the annual orders pre-experiment, and the cumulative number of orders pre-experiment. And then when we interact this with the treatment condition, we do not see any super meaningful interaction effects. If anything, like the treatment effect is quite stable across different experience levels. So it doesn't look like sellers' experience is driving this result. Okay, cool. Now on the static story, the question is demand elasticity different at different rankings, right? And so to understand that, what we do is we estimate how elasticity varies with rank. So we basically split ranks into 4 quartiles, and we run a pseudo-Poisson maximum likelihood Chen and Ross specification here to understand the price elasticity at different ranking positions. So the elasticity, and what we find here is the following. So the x-axis is the quartile. The y-axis is the price elasticity. So the bottom quartile is like lowest ranked products, and Q4 is the highest ranked products. And if anything, what we see is that the price elasticity based on our specification is quite stable over these ranking positions, right? And so if anything, the top products are less elastic and the prices should have gone up. So it doesn't look like a static story is explaining the data behaviors that we observe. And so the last story is the dynamic story. So let me pause here and basically try to explain the intuition we have. So technically what could be happening is sellers understand that if I price lower today, I attract more consumers, I attract more demand. And then once I attract more demand, my conversion probability is increasing, which is the prior for tomorrow's ranking, right? And now my tomorrow's posterior conversion probability is going to increase. And as a result, I will be better ranked tomorrow, right? So this is the intuition. I hope it's clear. Ron, I think you have a question.
Fourth explanation, so I don't know if
Sure, go ahead. We are happy.
So imagine you're like in the 5th page with 10 crappy sellers of price high, and then you're drawn to the first page with 9 sellers of price low. The best response is just to lower the price. They're not going to change anything, but you have to lower the price. So just a response to where you're thrown at. And I'm not sure the other 9 sellers in the top page will respond to you too much because you're kind of a small seller.
I definitely agree with that mechanism. One thing, which my immediate response, and I should think more about it, my immediate response is that sellers are not super sophisticated in the sense that I don't think they track the prices of neighboring products that much. So basically, if I'm thrown into lower price neighborhood, I might not even understand that at the beginning, right? So that is one explanation. And another thing is that the algorithm kind of retrains every 4 hours. So every 4 hours, because it basically updates the posterior every 4 hours. So every 4 hours, your neighborhood is changing. But I think we should do more analysis. Or you kind of think you have.
So if you're facing lower price competitors on the same page, that will be reflected in the residual demand elasticity of that product. Right? Your residual demand will rotate towards being more elastic. So I think that's baked in our elasticity. Okay, maybe
But I think there is a good point. But my immediate response is that because rankings change every 4 hours, it's very hard to track. And I don't think it's like Amazon where there is people or whatever where you could track your neighborhood.
I think it's testable, sorry.
Go ahead. Go ahead.
Just a little odd if they're tracking their ranking position and if the prices are shown on the results page.
But the prices of competitors is not. You don't know what your neighbor thinks.
The customer doesn't see the prices on the results page.
Sorry, it's seller.
Yeah, but don't you track your position as if you were a customer?
Oh, what I meant is that every seller has this account where they go and they see their ranking. Yeah. It's not like they're scraping every day.
Oh, they cannot see the prices of.
In the account, as far as I understand, no, but I would.
So scraping or something. Because then
Yeah, the scraping is a possibility. The problem is that again, like with 4 hours thing, it's hard to scrape.
How much meaningful variation do you have at the seller? Okay, some things are addressable, I will elaborate more. So how much meaningful variation do you have at the seller level in terms of exposure to the experiment? Because if this is correct, if this is the mechanism, you're saying, oh, I realize that if I price low now, there is gains that I can accrue in the long run. Right. Which means that if as a seller, I'm more exposed to the experiment, meaning that more of my products are treated, I should start cutting prices on other stuff as well, because I internalize the fact that, oh, I cut prices, it gains come, because I think that's what you're saying, right?
Yeah.
So maybe that supports your.
That's a good point. Like we can do the analysis based on the seller's intensity, like of treatment in terms
of other
products and spillover effects on other.
So I think that addresses, it's a testable.
Yeah, this is great. Thank you so much.
So we have roughly 5 minutes.
Yeah.
And we propose to let her finish.
That's okay. That's okay. I'm glad to hear it. Like I'll cut on the structural model part. So basically, your friend is looking at me with such blame. Okay, so on the structural model part, basically what we do is we write. We write a dynamic equilibrium model of seller pricing, and basically our goal is to understand does the model fit the data well or not? Because if the model with dynamics is fitting the data, that means that the dynamics is playing some role. And then the next goal is obviously to assess the platform's power over competition through this ranking algorithm. So what we're modeling is consumer demand, ranking algorithm, and sellers' pricing decisions. So the consumer demand, the impressions are modeled as a Poisson arrival process where the arrival probability is a function of the rank. Conditional on arrival, purchase probability is a binary logic, right? Which is a function, like the utilities are a function of prices and ranks. And so from the demand side, our goal is to estimate the price elasticities, the price coefficient, and the ranking effects. And then we're modeling the ranking algorithm. We know their algorithm, but we do need to model to run counterfactuals. And we approximate their algorithm with the beta binomial approximation that I basically explained to you previously. The only difference is that in reality, the platform uses a forgetting factor where part of the data gets forgotten, historical data gets forgotten, and it's going to be important in the counterfactuals. So basically, the idea is that if rho is very close to 1, then all data does not get discounted. The rankings are very sticky. If rho is very low, then all data vanishes quickly and rankings are volatile. On the seller side, we basically model this as a single agent dynamic pricing problem where the seller maximizes the discounted sum of future profits, and the seller state is the product's posterior and cumulative number of impressions. Right, so there is a dynamic entered here, and in terms of estimation procedure, let me skip this, but basically we use experimental data to estimate and methods of moments to estimate the demand and algorithm parameters, and then we solve the Bellman. Importantly, we leave out post-treatment prices for out-of-sample validation, and basically here what we see is we drop the outliers here. That's why the observed price response is minus 2.7% now. And basically, if in the simulation, in the out-of-sample validation, the model predicts a decrease of prices by 2.3%, which is very close to reality. Now, if we did not incorporate any dynamics, we would have gotten very little price change. It would be like only 0.5%. So it seems like dynamics does have a bite here, like it is important to match the data. So the investment mechanism is validated out of sample. And now towards the counterfactuals, our goal was to understand how much power does the platform have over the algorithm, like in competition on the platform. And so basically our estimated rho is 0.9941, which means that the data lives for 117 days. By the way, it really matches the data set the platform has. Like the data usually lives for 3-4 months. And basically what we do in the counterfactuals is we do a grid search to find a different rho that would lead to lower equilibrium prices. And we find that if data only survives for 23 days, then the equilibrium prices would have been lower by 8%, and the seller profit would have been decreasing, but then the consumer surplus and platform's revenue would go up. Okay, so basically the point here, the big point here is that one parameter, even without setting prices, can shift equilibrium prices by up to 8%. Okay, so the takeaway here, what I told you today, is that, and I can't believe I'm on time. So ranking algorithms do affect equilibrium prices, and exogenous ranking boost causes a 2.3% wholesale price decrease. The mechanism seems to be the sellers invest in future rankings, but we will look at what Ron is suggesting. And basically, from the policy perspective, people have to understand that even if you do not know the entire algorithm, you have to know that like just one parameter in the algorithm can really change the market equilibrium quite a bit. And I thank Song for agreeing to discuss our paper. Thank you so much for your feedback. Oh, I think you downloaded. Okay.
Okay.
All right, thank you very much and for the paper, and it's an interesting read, and so I enjoyed it quite a bit. So this let me first give it, because the paper, the presentation, there are so many questions, right? And I just want to give you a very high level discussion, right? I mean, a summary about what the paper is about, right? And with the main message that the author is trying to deliver, right? And so this is a major e-commerce platform, right? And there's thousands of products, and they're trying to show customers which one on the top, easier for them to find it out, right? And so you need to rank them. And so there is one experiment, right? And so the platform ranked the product based on their belief about the product quality. And so they ran one experiment, and there is an artificial boost of quality belief for 2% of the products, and which improve the product position on average by 167 points, positions. And so what's surprising about this experiment's outcome is supposedly if the product become higher on the rank, right? And supposedly they should have charged a higher price or at least to keep their steady. And because they are on a more premium spot. In contrast, what they found is that the seller cut their wholesale price, cut their prices by 2.3% on average. So the question is now why? And so where there are a lot of questions about the design of the experiment and the underlying settings, right? And so from what I read about the paper, I think the mechanism is actually quite straightforward, right? And so the authors did a good job in conveying that in the paper. And so the reason is that the true quality of the product is not really observed by the firm. Right. So what the firm does, the platform does, is trying to use past sales to infer what the true quality of the product is. And so in other words, the ranking is proportional to some kind of mean prior about the quality of each product, and the prior comes from past sales. Right. And then there is this row component. This row is the forgetting rate. And how many days in the past the sales and the firm will use to infer the quality. And so the row is how this algorithm and will update. And so that row is also the knob that the counterfactual will try to kill. And so now the logic becomes the following, right? And so because lower price today, and it means more sales today, and will boost the posterior belief of quality tomorrow, and hence you will get a better rank. And then when those products got treated and they were put at a higher position on the ranking on the page, they actually got a higher marginal return for lowering the price. Because when they add a more premium spot, 1% lower price, they got more sales when they are on the third page. So they got more incentive to lower their pay than otherwise. So that's the key reason why we see this 2%, 2.3% lower in terms of their prices. All right, and so that is the summary of the paper, and then the authors trying to tune that row, the forgetting rate. And so in the next few 10 minutes, and I will talk about 3 dimensions, right? And I don't think there are a lot of questions on all those dimensions, right? And so just hopefully that those will be helpful. Those will be marginally helpful, right? One is about the positioning of this paper, and the second one is the alignment, right? And this is actually buried in one of the footnotes, right? And it didn't come out in the presentation either, right? One is the modeling trade-offs and what are the modeling choices and pros and cons. So first, the positioning, right? And so there are 2 kind of ranking papers, and so algorithms that the ranking algorithm have price built in. And for example, the price directly affect how the platform rank their products, such as Amazon, right? And one of the most recent paper and by Lee and Mosov, as well as a couple of other papers, right? And so this is one line of the paper, right? And this paper, the price does not enter the algorithm, and the price only affect the ranking indirectly via the sales. And so this paper is one of the first structural model in the e-commerce, in the platform, e-commerce platform context to study this. So across these 2 types of algorithms, the welfare claims are quite different in kind, right? And not just in degree, which I will talk about in a moment, right? And on the next theme, right? And when I talk about the alignment part. And so the idea of travel, in my mind, I think it travel beyond e-commerce. And so this paper and the algorithm holds, basically the algorithm holds a belief about the agent, the agent's action, and then shape the belief agent and then act accordingly. And so this paper is the sales effect quality, and so the agent, the sellers, it just the price. Right, and then here I'm also shamelessly promoting my paper with Kao. All right, and so in the context of sponsor search, right, and where the search engine care about click-through rate, right, and so they will use the past click-through rate of a advertiser to approximate and how much click-through rate that they expect in the current view. So advertisers they will bid higher than the static optimal bid level, so that they have a higher winning probability and boost their position, and so that they got more click-through rate in the current days, and so increase their future winning probability. So I also see there are a few other contexts where this may happen, right? And where the common structure is, right, there are a few parameters in the algorithm summarize the belief, and the agent best response is to shape those parameters, right? So when they shape the parameter, they may affect the bottom line of the platform, but more importantly, they may affect the consumer surplus. And so that's where it may become interesting. All right, and so in particular, let me go to the second point that I want to make, right? And so it is buried in the footnote 7. And so I think it deserves a spotlight, right? And as turn out, this row that maximizes the profit of the platform also maximize the customer's profit at the same time, as customer surplus at the same time, right? And so why is that the case, right? It has something to do with the firm's the revenue of the firm, the profit of the firm, right? This is the wholesale platform, right? And basically they have they collect a proportion of the sale price and of the retail price at the end of the day, right? So in this case, and also the markup does not change much, does not change at all with the ranking. And so in this case, a lower row and lead to more sales, so more revenue for the platform. At the same time, it also lower price and the higher customer service. And also, I noticed that the price elasticity is 4.5, right? And so that is actually give a lot of space for the row to adjust, right? So that's why these two coincide with one. Right. And so this directly, and it's a consequence how the platform gets paid. So if you think about the algorithm, right? And so it also the revenue, the contract, the revenue between the platform and the agent, right? And for Amazon, for example, this will for this one, this work. For Amazon, right? And such as say either vertically integrated or around retail at the same time, this may not work. And also if it's attention-based, this may not work either. So why do I want to point this out? Because there is some extrapolation point that I want to make, right? And probably a bit far-fetching, but I think it may be interesting to talk a little bit about how the contract structure between the platform and the agent. And in the vintage point of how legislation on platforms, the algorithm disclosure, because this is something that a lot of legislation discussion about, right? Whether the algorithm should be disclosed, right? So that it makes it more transparent, right? Sometimes this legislation matters, sometimes this legislation doesn't matter, right? And that will affect the seller's profit as well as the consumer surplus. So this is one thing that I want to talk about. And so this is a segue to lead to the next the pros and cons and of some modeling choices, right? And so when this alignment would work, so why it won't. So Amazon, when there's retail, there's 3P commissions, there are ads, it won't work. And so also if seller can exit, and also, if a seller can exit, it won't work. And also, if you adjust the row, and the one thing that you notice, the seller profit at the optimal row that you calibrated dropped 16%. So why seller? I mean, even if sellers they don't exit, what if they lower the price of the product to to compensate. So that's one problem, right? And so this is not a problem for your case, right? The elasticity does not vary by rank, right? And you test this out empirically. So now let me finally talk about the choices of some of the model choices, right? And elasticity, you tested it out, right? Elasticity does not vary with rank, right? If it does, right, and the model may not work. And stationary equilibrium, and so here there's one extrapolation because you only treated 2% of the cost of the sellers, right? Counterfactual actually expanded to the whole 100% of all the sellers, right? And so this will we need to put some face on the model structure, right? And so that's one thing, right? And also there is one thing that I think it did not come out very transparently in the presentation is there is this approximation of the true algorithm, right? Let me get this quickly cover this, right? And so the real algorithm the platform use is Thompson sampling, right? And you use the beta Bernoulli, right? And Thompson sampling, and the one feature of Thompson sampling is that it put a lot of it gave more boost when there are a lot of uncertainty, right? And so product with uncertain quality belief get a higher boost. But the approximation is a mean belief. There is no noise. And why it matters? Because one of the sharpest finding is younger products, newer products. Also, the product has less sales at the third page, fourth page. And so they are more likely to be treated. And so they also got more noise. And so that may somehow make the young products got higher, is more reactive, got a higher treatment effect, right? And that become something to ponder upon. Okay, so this is not a question, but I think it deserves more robust check. Right, and in short, and I think this is a very good paper, and you have a rare data access, great opportunity, and a very clear algorithm. You observe everything, and so that's great. And so worth further consideration, and one is the quality change and the seller exit, right? Especially given there's a 16% drop in their profit. And another one is whether the Thompson sampling and whether it will contaminate your result, right? One of the sharpest finding that you have. Okay, that's all.
Thank you so much. I won't take up anyone's time. I'm just going to say that thank you so much, everyone. And to Song too, I really like the points about the both Thompson sampling and seller text, and we're going to do that. Thank you.